geopolitical friction in the Baltic Sea has forced a permanent structural realignment of Russian bulk commodity exports. The Baltic is now a NATO-dominated waterway, rendering traditional corridors highly vulnerable. Consequently, Moscow is executing a capital-intensive pivot toward the Arctic. The data shows a clear divergence. Baltic port bulk exports fell 36.7% between 2021 and 2024, dropping to 71.1 million tons per annum. Meanwhile, Murmansk bulk throughput expanded 15.5% to 64.8 million tons. This represents a structural shift rather than a temporary market fluctuation. The compound annual growth rate for Baltic terminals is -14.2%. In contrast, the Arctic corridor shows a steady 4.9% expansion. Building marine terminals is insufficient without matching overland logistics. The new Lavna coal terminal features a design capacity of 18.0 million tons per annum. However, initial throughput is severely restricted by linear rail infrastructure. The primary physical bottleneck is the 46-kilometer Westkola rail link and its 1.3-kilometer bridge over the Cheloma River. This single-track bottleneck caps initial capacity at 9.0 million tons. Full double tracking and electrification must be completed to unlock the remaining terminal capacity. Projected actual throughput is modeled to scale from 4.5 million tons in 2024 to 18.0 million tons by 2030. This timeline depends entirely on the synchronization of the broader Oktyabrskaya railway network upgrades. The strategic value of Murmansk lies in its unique hydrographic profile. Located on the ice-free Kola Bay, the port features a 20.0-meter deepwater draft. This allows unrestricted loading of Capesize vessels up to 150,000 deadweight tons. In contrast, Baltic ports face severe physical limitations. St. Petersburg is restricted to an 11.0-meter draft, capping vessel sizes at 40,000 deadweight tons. This shallow draft increases per-ton shipping costs by forcing the use of smaller vessels for long-haul Asian routes. Furthermore, Baltic and Black Sea routes remain vulnerable to maritime choke points like the Danish Straits and the Bosporus. Murmansk bypasses these geopolitical bottlenecks entirely, offering direct access to the open ocean. This infrastructure push mirrors the historic Murmansk run of World War II, where the Kola Bay served as a vital ice-free lifeline. The commercialization of solid-state batteries is fundamentally bottlenecked by the physical metallurgy of lithium. Lithium is extremely soft and highly cohesive. During mechanical reduction, the metal adheres aggressively to work rolls. This causes surface tearing and catastrophic foil breakage at thin regimes. The data reveals a severe yield collapse as foil thickness decreases. At 50 microns, mechanical yield is 98.5%, and scaled down to 10 microns, yield drops to just 12%. This collapse is driven by high tensile stress and roll adhesion tearing. Simultaneously, defect density spikes exponentially. Defects rise from 0.12 per square meter at 50 microns to 35.0 at 10 microns. Solid-state designs require foils under 20 microns to exceed 400 watt-hours per kilogram. This forces production directly into this low-yield, high-defect regime. Lithium's extreme chemical reactivity introduces severe thermodynamic constraints. The metal reacts spontaneously with atmospheric moisture and nitrogen. This forms highly resistive passivation layers of lithium hydroxide and lithium nitride. These layers degrade the electrochemical performance of the anode. To prevent degradation, manufacturing must occur in ultra-dry environments. At a standard dew point of -30 degrees Celsius, the passivation layer grows at 1.25 nanometers per minute. Lowering the dew point to -60 degrees reduces this growth to a negligible 0.004 nanometers per minute. However, this environmental control imposes a nonlinear economic penalty. Operating expenses increase 6.8 times when moving from -30 to -60 degrees. This is driven by the extreme energy demands of multi-stage desiccant wheel regeneration. Manufacturers face a stark trade-off between throughput, capital cost, and foil thickness. Mechanical rolling is the current industry baseline. It offers high line speeds of 15 meters per minute and a low capital cost of $12.5 million per gigawatt-hour. However, it is physically limited to a minimum thickness of 20 microns. Alternative deposition methods bypass this physical limit but introduce severe economic penalties. Physical vapor deposition can produce layers down to 2 microns. Yet, It requires high vacuum systems that slow line speeds to 2.5 meters per minute. This drives capital costs up to $45 million per gigawatt-hour. Molten lithium coating represents an emerging compromise. It achieves 10-micron thicknesses at 20 meters per minute. However, this process requires complex surface tension management and high-temperature liquid lithium handling. This manufacturing bottleneck is structurally analogous to early 20th century aluminum rolling, which required specialized multi-roll cluster mills to overcome similar tensile failures. The commercialization of high-field magnet technologies depends on second-generation high-temperature superconducting tapes. These tapes require near-perfect crystalline alignment on a flexible metal substrate. This alignment is achieved by depositing a nanometer-thin template of magnesium oxide using ion beam-assisted deposition. The manufacturing process is constrained by a severe throughput mismatch. While substrate electropolising operates at 150 meters per hour, the critical texturing step is limited to 60 meters per hour. The active superconducting layer deposition is even slower, running at 20 meters per hour. Although the active layer deposition has the lowest linear speed, the texturing step is the primary structural bottleneck. Any crystalline defects introduced during texturing propagate through all subsequent layers, ruining the tape. Furthermore, the high vacuum systems required for these two steps account for over 75% of total capital costs. The scaling of commercial fusion energy has created an unprecedented demand shock for superconducting tape. Private fusion startups require massive quantities of tape to construct compact, high-field tokamaks. This demand is scaling exponentially, far outstripping current industrial capacity. The data illustrates a widening structural deficit. Global production capacity is projected to grow from 1,200 kilometers in 2020 to 18,000 kilometers by 2028. This represents a 40% compound annual growth rate. However, cumulative fusion magnet demand is projected to reach 78,000 kilometers over the same period. This mismatch creates a structural deficit of 60,000 kilometers of tape by 2028. The bottleneck is physical, rooted in the low throughput of existing reel-to-reel vacuum chambers. The throughput bottleneck cannot be solved by simply increasing the speed of the tape through the vacuum chamber. The development of crystalline alignment is a nucleation process governed by precise ion-to-atom arrival ratios. Attempting to accelerate the process destroys the template structure, increasing the deposition speed from 0.5 to 4.0 meters per minute. Causes the crystalline alignment spread to degrade from 2.8 to 8.5 degrees. Once this alignment spread exceeds 4.3 degrees, the critical current density of the superconducting layer drops to near zero. This thermodynamic limit forces manufacturers to operate within a narrow window of 1.0 to 2.0 meters per minute. This physical rate limit prevents rapid scaling of production. This bottleneck is structurally identical to the early days of optical fiber manufacturing, which was constrained by low vapor deposition rates until new axial deposition methods emerged. Advanced semiconductor manufacturing relies on atomic layer deposition to build sub-7 nanometer transistors. This process requires trimethylaluminum, an extremely volatile and pyrophoric organometallic precursor. The global supply chain for this chemical is highly consolidated and operating near its physical limits. The data shows global demand scaling from 120 metric tons in 2018 to a projected 300 tons by 2026. This expansion is driven by the transition from FIN FET to gate-all-around architectures. These new designs require up to 35% more atomic layer deposition cycles. Consequently, the reserve capacity margin is collapsing. The gap between global demand and total capacity has compressed from 33.3% to a projected 3.3%. A triopoly of chemical producers controls 87.1% of this capacity, creating an acute single point of failure risk. Sub-7 nanometer fabrication cannot tolerate metallic impurities. Transitioning from 6N to 9N purity reduces metal contaminants from 1,000 parts per billion to less than 1 part per billion. This extreme purity is required to prevent charge trapping in gate oxides. The operational impact of precursor purity is nonlinear. Dropping from 9N to 8N purity causes gate oxide breakdown yields to fall from 98.4% to 89.7%. This 8.7% drop represents a catastrophic loss in wafer-level profitability. Achieving 9N purity requires multi-stage vacuum distillation and a duct purification. This process reduces synthesis yield by up to 40% compared to industrial-grade alternatives. The physical chemistry of purification limits the volume of viable precursor available to advanced fabs. Synthesizing high-purity precursors is only the first bottleneck. Transporting pyrophoric chemicals requires specialized, heavy-walled stainless steel class 4.2 isocontainers. The global fleet of these containers is failing to keep pace with semiconductor expansion. Between 2020 and 2024, the container fleet grew 24.4%. Meanwhile, the number of active advanced fabrication facilities surged 56.2%. This deficit leaves the logistics network highly vulnerable to transit delays. Furthermore, air freight is banned due to the pyrophoric nature of the chemical. Fabs must rely on ocean shipping, where transit lead times spiked to 82 days in 2022. To mitigate this volatility, facilities must maintain 60 to 90 days of safety stock, locking up the limited container fleet. This vulnerability mirrors the silane gas shortages of the late 1980s. In that instance, an accident at a single Japanese purification plant halted global semiconductor packaging. Today, the highly consolidated trimethylaluminum supply chain presents an identical systemic risk. The geography of European trade is governed by a stark thermodynamic reality. Routing container vessels from the Suez Canal through the Adriatic Sea to the port of Trieste bypasses the Iberian Peninsula entirely. This shortcut reduces the maritime transit distance to Central European industrial hubs by exactly 2,000 nautical miles. The operational savings are immediate. Maritime transit times drop by 4.3 to 5.0 days. This acceleration lowers capital in transit costs and optimizes container fleet utilization. Furthermore, the shorter voyage reduces fuel consumption by 129 to 150 metric tons of heavy fuel oil per trip. This represents a 28% reduction in maritime emissions. Trieste is the most thermodynamically efficient southern gateway for Central Europe. The maritime efficiency of the Adriatic route is currently lost at the Alpine barrier. The overland rail infrastructure traversing the Alps faces severe physical and mechanical constraints. Steep mountain gradients of up to 2.6% limit trailing loads to just 1,100 tons. These steep inclines require expensive auxiliary helper locomotives to push freight trains over the summits. Furthermore, short passing sidings restrict train lengths to between 550 and 600 meters. This falls far short of the European intermodal standard of 740 meters. Loading gauge restrictions also prevent the transport of standard 4-meter-high high-cube containers on standard pocket wagons. To unlock Trieste, the European Union is investing in massive engineering bypasses. The Semmering base tunnel will reduce gradients to 0.85% and eliminate the need for helper locomotives by 2030. The structural transformation of the Baltic-Adriatic corridor is mapped to specific infrastructure milestones. Port of Trieste container throughput is projected to scale from 0.85 million TEUs in 2024 to 1.60 million TEUs by 2030. This represents an 88% volume expansion. To handle this influx, the rail modality share of hinterland traffic must rise from 52% to 66%. This shift transfers the primary transport burden from congested highways to the rail network. The opening of the Koralm Railway in late 2025 will provide the first major capacity relief. By 2030, the commissioning of the Semmering base tunnel will more than double Alpine rail transit capacity to 35.0 million tons per annum. This capital-intensive push mirrors the mid-19th century construction of the original Semmering Railway. Once again, European trade velocity is bound to the physical engineering of the Alpine passes. Transition of power electronics from silicon to silicon carbide is constrained by solid-state physics. Silicon carbide possesses a wide bandgap of 3.26 electron volts and a breakdown electric field 10 times higher than silicon. These properties reduce energy losses in electric vehicle inverters by up to 70%. However, the physical chemistry of crystal growth imposes severe thermodynamic limits. Unlike silicon, which is grown from a liquid melt at 1425 degrees Celsius, silicon carbide has no stable liquid phase at atmospheric pressure. It sublimates directly from solid to gas at temperatures exceeding 2,000 degrees. Single crystal substrates must therefore be synthesized via physical vapor transport inside a graphite crucible. This sublimation process is exceptionally slow. The growth rate for 200 mm silicon carbide is 0.20 mm per hour. This is approximately 125 times slower than conventional silicon Czochralski growth. A single Boule run requires up to 240 hours of continuous thermal stability. The extreme thermal environment also introduces severe thermoelastic stresses. Operating at 2350 degrees with steep thermal gradients of 45 degrees per centimeter causes structural defects. These stresses frequently lead to wafer cracking during the slicing process, limiting throughput. Scaling silicon carbide manufacturing requires transitioning from 150 mm to 200 mm wafers. Historically, this transition has been hindered by low yields and high defect densities. Basal plane dislocations propagate into the epitaxial layers, causing premature device breakdown. The data shows steady but difficult progress. 200 mm wafer yields have improved from a non-viable 5.0% in 2018 to 51.0% in 2024. This progress was driven by advanced thermal field modeling in physical vapor transport reactors. Simultaneously, basal plane dislocation density has been reduced by over 90%. Defects fell from 9,500 per square centimeter to 850. This brings the material close to the critical threshold required for high-voltage device reliability. Despite these improvements, a 33% yield gap remains between mature 150 mm lines and emerging 200 mm lines. This gap maintains a steep cost premium for larger substrates. This scaling bottleneck is structurally analogous to the synthetic quartz shortages of World War II, which required entirely new hydrothermal autoclave technology to resolve. The global transition to green steel is fundamentally constrained by raw material chemistry. Direct reduced iron technology requires ultra-high-grade ore with extremely low impurities. Standard blast furnaces can process lower-grade ores, but electric arc furnaces cannot tolerate high silica and alumina levels. This chemical threshold makes high-grade deposits highly strategic. The price spread reflects this structural shift. The premium for 67.5% iron ore over the 62% benchmark expanded 71.4% between 2018 and 2024. This quality spread reached $78 per dry metric ton. Global supply of this premium material is highly consolidated. The Labrador Trough in Canada and Brazil's northern system control over 80% of seaborne export capacity. This concentration makes the subarctic logistics corridor of eastern Canada a critical macroeconomic choke point. Translating geological wealth into industrial input is bottlenecked by land-based infrastructure. The port of Sept-Îles possesses a deepwater marine terminal capable of loading massive Chinamax vessels. However, the dry land unloading systems cannot match this marine capacity. The primary physical bottleneck is the Pointe Noire rotary car dumper. This system is operating at 26.8 million tons per annum. This represents over 95% of its hard mechanical design limit of 28.0 million tons. While the dock can load ships at 8,000 tons per hour, the upstream rail-to-storage transfer rate throttles total throughput. Resolving this constraint requires a capital expenditure of 350 million Canadian dollars. This Phase 2 expansion will install a second rotary dumper to unlock an additional 15 million tons of annual capacity. Nominal logistics capacities are highly misleading in subarctic environments. Extreme winter weather imposes a severe, non-linear physical penalty on rail and material handling systems. Below -30 degrees Celsius, steel rail brittleness forces a 37.5% reduction in train length. Dumper cycle times also degrade as frozen ore adheres to the rail cars. Unloading times spike from 45 seconds to 140 seconds per car. Furthermore, frozen ore lumps increase the reject rate at the grizzly screen to 12.5%. These winter disruptions reduce net port throughput by up to 30% between December and March. This logistical bottleneck is structurally analogous to the late 19th century development of the Mesabi Iron Range. There, the rapid scaling of American steel was bound to the rail capacity of Great Lakes ports, forcing a complete re-engineering of bulk material handling. Sweden's transition to fossil-free steelmaking is fundamentally constrained by shallow water. The northern Norrbotten region requires massive bulk export capacity to ship green direct reduced iron to European markets. Currently, the port of Luleå is limited by a 12.3-meter channel depth. This restriction caps vessel sizes at 55,000 deadweight tons. Project Malmporten addresses this physical bottleneck by dredging the channel to 15.0 meters. This allows Baltic-Max-class vessels of up to 160,000 deadweight tons to load fully. Consequently, annual port capacity will scale from 8.1 million tons to 22.5 million tons by 2030. This represents a 177.7% increase in bulk handling capability. The project requires excavating 22 million cubic meters of till and clay, making it the largest maritime dredging project in modern Baltic history. Dredging alone cannot resolve the seasonal realities of the subarctic. The port of Luleå faces an average of 150 days of ice cover annually. Without assistance, winter ice reduces shipping capacity by up to 84.6% in February and March. Active icebreaker escorts mitigate these losses, maintaining throughput at 69.2 to 80.0% of baseline levels. However, this introduces a critical dependency on Sweden's aging stay-tone fleet. This fleet consists of 5 Adel-class icebreakers constructed between 1974 and 1977. A single day of mechanical failure or delay during the freeze creates an immediate backlog. This backlog ranges from 15,000 to 20,000 tons of steel products daily. Such disruptions directly threaten just-in-time automotive supply chains across Central Europe. The physical capacity of the port of Luleå is the absolute rate-limiting step for Northern European industrial decarbonization. By 2028, regional green steel and hot briquetted iron production is projected to reach 10.0 million tons per annum. This volume exceeds the unexpanded port baseline of 8.1 million tons by 23.4%. Without Project Malmporten, a structural export deficit of 6.9 million tons will emerge by 2030. Exporters would be forced to rely on expensive, carbon-intensive overland rail to southern Swedish ports. The expanded capacity of 22.5 million tons provides a necessary 50% buffer. This infrastructure bottleneck is structurally analogous to the late 19th century industrialization of Germany's Ruhr Valley. The landlocked steel mills of the Ruhr required the canalization of the River Ruhr and the construction of the Dortmundems Canal to access global markets. Today, the decarbonization of European heavy industry is similarly bound to the physical dredging and ice-breaking capacity of the northern Baltic.